This video contains the solutions for your multiple choice practice for first half of chapter 5. First one here. For what value of k will x plus k over x have a relative maximum at x equals -2? Well, relative maximums and minimums happen when derivatives are 0. So let's make a little room for ourselves here. So let's just call that y equals x plus, I'm going to call that kx to the -1. The derivative of that would be 1 minus kx to the -2. And I want it to be to have a maximum, be a horizontal tangent line, right? So in other words, where that's equal to 0. So 1 minus kx to the -2 equals 0. And they're telling us that we want it to happen at x equals -2. I'm going to go ahead and plug that in. So 1 minus k times -2 to the -2 equals 0. That's, let's see, how are we going to deal with that? 1 equals, I'll add this to the other side, equals k times, and let's see, -2 squared is 4. The negative would flip it over, it'd be times 1/4. So k is equal to 4. That'd be D. All right, here's a thinky problem for you. Got two functions, f and g, and f prime of g is always greater than g prime. F prime of x is always greater than g prime of x for any x. What does that mean? That means to me that this one's always steeper, right? The derivative of this, its slope, if you want, is always greater than this. So I imagine like the f function is something like this, and the g function is something that's always less steep, right? Well, what could happen here? I think there's two things that could happen. It's possible that if like the f function, for example, were like e to the x, and if the g function were something that always had a smaller slope than that, like it could be even a horizontal line like that, right? They could never intersect, right? That's possible. It's possible that they do not intersect. But it's also possible if the g function, just because we're talking about its slope, it could be up here. It could still always have a smaller slope, but just be up higher so that they crossed once. Could they cross more than once? Well, I think once they crossed, this one's always going to out-steep its buddy here. So I think that it couldn't ever come back. So I think it could either cross 0 times or 1 time. So I like both of those, but I think it's got to be both. So intersect no more than once. That I think means no times or 1 time. And so we think that they couldn't intersect more than once, right? And have a common tangent at each point of intersection. That's crazy talk. So I think B is the correct answer. Oh, here's a super easy one. Come on, you're gonna like this. If y is a function and it's increasing but concave down, its derivative is positive, second derivative is negative. So it's increasing but bending down. Hey, that was fun. This one, these two are not in the running because this one has changing concavity and changing derivative. I mean, this one has a derivative that's positive and then negative, right? Increasing, decreasing. This one's increasing, but it looks like it's concave up and then concave down. So anyway, it's B. That was fun. That made me feel really smart. All right, so how about this? A point of inflection. Well, riding the wave of smartness here. Points of inflection, that's where the second derivative, I'll write it as y here, sorry, y double prime equals 0, right? Now that doesn't guarantee it, but that's a real good way to go snooping around for points of inflection because we want it to cross from positive to negative, right? So let's find our second derivative and see what happens. I'll use this little space up here. First derivative would be 20x cubed minus 5x to the fourth. Second derivative would be 60x squared minus 20x cubed, setting that equal to 0 and factoring out a 20x squared. Give me what? 3 minus x. Okay, so where are the possible zeros? At 0 and at 3. So make my little number line. Remember, this is don't jump too fast into that answer, because we got to check and make sure the signs really do change. So try something below 0, like -1. -1 squared is +1, 20 times 1, and -1, that would be positive. And then try something in here like 1. 20 times 1, 3 times 1, that's oh, look, ha ha ha, it didn't change sign. Well, remember, when you have like double roots or even roots to even powers like that, they don't cause sign changes. And then if you try something above 3, like 4, you get positive. 3 minus 4 is negative. So it looks like the concavity, the sign of the second derivative, changed at 3. So that's B. All right. At x equals 0, which of the following is true of the function f defined by this? Well, let's see. It's increasing, decreasing, is this discontinuous? That means it's got like a hole or a jump or vertical asymptote, and I think you can plug anything into that, right? E to any power, that's all good, and x squared's good, so I think that it's definitely continuous. Minimum, maximum. Well, look, increasing, decreasing, minimum, maximum, those are all things about the derivative, so I think that's what we're supposed to find here. That's 2x. The derivative of this, derivative of e to the whatever, is e to the whatever times the derivative of what's inside, which is -2. So there's your derivative. You can set that equal to 0 to try to figure out where maximums and minimums are. And I guess you could factor a 2 out. But then this gets a little tricky. You really just have to kind of think about this one, because without a calculator, I don't think we're going to be able to find what makes this equal to 0. But I think it does have a spot where it's equal to 0. So I think if you think about like going way into the negative numbers, this would be some negative number, and then e to the -2 times big negative number, that would be positive. E to some big positive number is a big positive number. So if you have a negative x minus another big number, that would definitely be negative for a while, right? Way over there. And then also, if you go into positive numbers, if this were some like big-ish positive number minus e to the negative positive number, that flips that over, and that makes it get very, very small. So you'd have big positive number minus tiny, tiny little thing. So I think that even though we don't know exactly where it crosses, we can see that it's going from being negative to positive. That's pretty tricky, but you can reason through that. And negative to positive means we're decreasing to increasing, so this would be a minimum. So it's got a minimum. Tricky. If you can figure out what these graphs look like, that's another way to see that they switch places. You know that y equals x looks like this, and e to the -2x. The negative sign is exponential, but it flips it around like this. So you can see that they flip like this, and here in the negatives, these are negative, and if you subtract this one, which is bigger, you still get negative, and then over here, you get this big one minus that one, you still have a positive. So that's another way of reasoning through that. All right, let's do something a little easier. If a function is continuous for all x, it's continuous. Let me give you a tip here. When I talk about functions that are continuous, you need to automatically think about things that are continuous but not differentiable. They're not telling us that it's smooth here. They're just telling us that it's continuous. So I always think of like an absolute value function or something with a corner in it, because that would be continuous but not differentiable. So that's a good example to think of. For all x, and it's got a relative maximum at -1, 4, -1, 4, and a relative minimum at 3, -2. So it's getting from here to here. Which of the following must be true? Does it have to have a point of inflection somewhere here? No, I mean it could be like some jaggedy, pointy thing like this, and that's continuous, right? There's your maximum, there's your minimum. So it doesn't have to have a point of inflection. Does f prime of -1 have to be 0? No, because it could be a sharp corner there. Could be not differentiable at all. Does the graph have a horizontal asymptote? What? I don't think so. Does the graph have a horizontal tangent line at 3? No, same thing as this. It could be a sharp corner, right? And does the graph have to intersect both axes? That's true, right? Because if you're going to get from here to here, you've got to cross this and this. The crossing the x-axis, that's like the intermediate value theorem. Remember that, right? If it's continuous, it's got to cross all y values. And I mean, if it's continuous for all x, then obviously it's got to cross this, right? Because its domain is all x values. So that's E. Again, if you see continuous, you think of something that's continuous but not differentiable. What are the coordinates of the inflection point on the graph of this? Let's see. Inflection point is second derivative. I'm going to need a little room to do that. So I've got y equals x plus 1 times tangent inverse x. That's a product for all you rule flaunters out there. So derivative of the first, which is 1 times the second, plus the first times the derivative of the second. All right. Second derivative. Derivative of tangent inverse is 1 over x squared plus 1 plus, I'll just put that on top here and do quotient rule on this. So that's low d high is 1 minus high. Sorry, can you see what's going on there? Minus high d low over low low. Okay, let's see. And we want to know inflection points, so I'm going to set that equal to 0. I'm going to get a common denominator here. The common denominator between this and this would be this thing squared. So I'm going to multiply the top and bottom of this by x squared plus 1, right? It's the same thing, x squared plus 1. And then we got plus x squared plus 1 minus 2x squared minus 1 all over x squared plus 1 squared. And if we want this to be equal to 0, that's only going to happen when the top is 0. So let's see if we can clean that up. We've got x squared plus x squared minus 2x squared. Those are gone. 1 hold on. I've got one thing wrong here. When I got from here, minus 1 times 2x. I think that's supposed to be minus 2x right there. Is it not? Yes, sorry about that. Okay. I was panicking because all my variables were jumping ship there. X squared, minus 2x squared. Those are gone. I got plus 1, minus 2x. So that happens when x is equal to 1. Okay, so I got my x coordinate. Now they want to know what are the coordinates of the inflection point on the graph of this. Well, if you want the coordinate, I know it's 1 comma something, right? But which was the right one? Well, I've got to plug, to get the y coordinate, I go back to the original function. So plugging 1 in here, that gives me 2 times tangent inverse of 1. What angle has a tangent of 1? Pi over 4 does. So 2 times pi over 4 is pi over 2. So it's e. Okay. The derivative of this attains its max. Well, if you want to talk about the maximum on the derivative, let's just find the derivative first. F prime of x would be equal to 4/3 x cubed minus x to the 4th. They want the maximum of the derivative. So let's just pretend that's original. If we were trying to find the maximum of this, we'd take its derivative and set that equal to 0. So I actually want to find what the second derivative is 0, because they're asking for the maximum of the derivative. That's an inflection point. Is it not? That's 4x squared minus 4x cubed. Set that equal to 0. Factor out 4x squared x minus, 1 minus x and let's see, that happens at 1, right? How do we know that? I should do the number line, shouldn't I? Can't just say that that's 1. So let's see, that would be 0 and 1. So 0 and 1. We're testing points here in the second derivative. So test something negative. 4 times negative thing squared is positive. 1 minus negative 1 that's positive. Test something like 1/2, positive, positive, didn't change at the squared factor. And then try something bigger, 1 minus 2, negative, that's positive. So looks like we're going maximum value, you get positive, increasing, decreasing, increasing, increasing, decreasing. So there's your maximum at 1. Here, given the function defined by find all values of x for which the graph is concave up. So second derivative again, 15x to the 4th minus 60x squared. Who comes up with these functions anyway, huh? Have to get paid well. X cubed minus 120x. Factor that. Let's see, that'd be 60x times x squared minus 2. So that's equal to 0 at x equals 0 and plus or minus the square root of 2. So let's make our number line. Negative square root of 2, 0. By the way, you're way too grown up here to forget these anymore. That's just ridiculous. Okay, so let's try a number that's less than negative square root of 2, like negative 2. 60 times negative 2 is negative. Negative 2 squared is 4, minus 2 is positive. Negative times positive is negative. Try a number like negative 1. That would be negative. That would also be negative. Let's see. There's no square. I know this x is getting squared, but it's not the whole factor that's getting squared like in this problem here. So we should expect sign changes every time, but we'll check to make sure. Plug in a 1 here. That's positive. Negative. And then plug in a number like 2. That's all positive. So where's it concave up? Here and here. So that'd be from negative 2 to 0, negative square root of 2 to 0, or greater than, yep, that's right, that's B. Alrighty. This is kind of like a pre-calculus question, I guess, but if you think about this, the sine function dropped by 1/2. Sine function usually does its thing from 1 to negative 1, but now it's been dropped by 1/2. So instead of going all the way up to 1 and down to negative 1, it's now going up to 1/2 and down to negative 3/2. But of course, if you put the absolute value signs around it, that's going to take any negative piece of it and flip it up above the x-axis, right? It just makes everything positive. So instead of going all the way down to negative 3/2, it'll attain that as its maximum. There isn't really a whole lot of calculus to do there, at least not as I understand that problem. That's how I would think about it. How about this? If f is a continuous function on a closed interval from a to b, which of the following is necessarily true? Okay, like the problem before, it's continuous, but they didn't say it's differentiable, so it could have a sharp corner. So I don't know, you could imagine something here like here's a to b, right? That's a continuous function from a to b. Okay. Does the derivative have to exist everywhere? No, there could be a sharp corner because it only says it's continuous. If there's a maximum, does the slope have to be 0 there? Nope, because we can have sharp corners. Let's see. The limit as x approaches x sub 0, so like some x sub 0 here, right? As x approaches that, f of x, is that equal to f of the limit as x approaches x is, well, look, this limit right here, as crazy as this looks, the limit as x approaches x sub 0 of x is just, that's just x sub 0. I mean, you can just plug the x sub 0 in here, right? There's nothing weird going on there. So that's saying that the limit as x approaches some number of the function is just f of that number. In other words, that's like the limit as x approaches c of f of x is equal to f of c. That's one of the criteria for a function being continuous. In other words, as you come in here and approach some value, you actually get the function value. In other words, you don't have like a hole there. No funny business. So that is actually true. Now let's say you couldn't make heads nor tails of that. Let's see if we can at least eliminate the other two. Does the derivative have to be 0 somewhere? No. I mean, this could just have been a straight line, right? Well, certainly the derivative doesn't have to be 0. Does the graph of the derivative of this have to be a straight? No. I mean, this is any function from a to b. Who knows what it looks like? Certainly the derivative doesn't have to be a straight line. So you could maybe eliminate your way to that answer too. All right. We want to find where is this function increasing. Well, it'll be increasing where the derivative is positive. So let's see if we can do that. Find the derivative and do the number line game. Derivative would be 1 minus 1 over x squared, right? That's x to the negative 1, right? So deal with that. So let's see, that's setting that equal to 0. And doing a little bit of algebra, you get x equals plus or minus 1. All right, so let's set up our number line. Negative 1, positive 1, and we want to plug some numbers in here and see what we get. If you plug in, notice you can't plug in 0. If you plug in something like negative 2, you get 1 minus 1 over negative 2 squared is 4. 1 minus 1/4 is a positive number. If you plug in something in between negative 1 and 1, like 1/2, you get 1 minus 1 over 1/2 squared is 1/4. 1 over 1/4 is 4. 1 minus 4, that's a negative. I talked my way kind of fast through those. You should slow down and check them more carefully if that's too fast for you. And then 2, 1 minus 1 over 2 squared, that's positive. So where is it increasing? When the derivative is positive, that would be here and here. So that looks like this. Right, from negative infinity to negative 1, and from 1 to infinity. All right, let g be a continuous function on the closed interval from 0 to 1. Let g of 0 be 1, that's the point 0, 1, and g 1 is equal to 0. So it's continuous from here to here. Ooh, that sounds like intermediate value theorem. It's got to cross all those lines, right? Okay, which of the following is not necessarily true? Does there have to be a number h in here such that g of h is bigger? In other words, does it have, and this means it has an absolute maximum. There's some value where you get the biggest function value for the whole interval. Well, that's true. If this is a closed interval, somewhere it's got to hit its maximum value, right? It's got to have an absolute max. If it's an open interval, it doesn't have to, because then you could have like an asymptote situation. But if it's closed, it's got to somewhere hit a max. So that's true. For all a and b, if a equals b, then g of a equals g of b. Well, yeah, I think we could have known that in like Algebra 1. I mean, if a equals b, then g of a equals g of b. Sure. There exists a number such that g of h equals 1/2. Does it have to cross the line 1/2? Sure does. That's the IVT, baby. Intermediate value theorem. It's got to cross all the y values. So that is true. But does it have to cross 3/2? Hey, that's up here. That's trying to be the IVT, but it picked a value that's too big. So I think that is not necessarily true. Let's just check the last one. Is it true that the limit as x approaches h? This is just like 2 problems ago. This is part of being continuous, right? The limit as you approach something actually has to be what you get when you plug that something into the function. Otherwise, you'd have a hole there. So that's part of being continuous, and they said it's continuous. So D, no dice. Boy, this is a long video. All right, we're almost there. Which of the following is true about the graph of this in the interval from negative 1 to 1? Increasing, minimum, those sound like derivative type things. Concave down, second derivative, asymptote. All right, let's see if we can figure this out. So there's some stuff about the derivative and the second derivative. Remember, don't be thrown off by absolute value signs in log functions. It just makes the domain bigger. The derivative of this is still 1 over that times the derivative of what's inside. Absolute value signs just go away. It just extends the domain. Second derivative, let's see, it's low d high minus high d low over low low. And we'll simplify that. 2x squared minus 4x squared is minus 2x squared minus 2. And I will simplify one more step. I'll bring that down here, sorry. So I'm just going to factor the negative 2 at the top. All right. So I got my derivative, second derivative. let's see. This says it's increasing, and if they just say it's increasing, they would mean it's always increasing. Is that true? Is this always positive? I don't think so. I think that certainly, like for values bigger than or less than -1, like -3, this would be 9 minus 1. This is negative, so that's not true. Is there a relative minimum at 0, 0? Let's see. At 0, 0, it looks like this would be 0, right? And we could check the sides. I think we kind of did that, didn't we? That on, let's see, on that side, like we could try something like, oh, let's see, it's more complicated, isn't it? That's 0, and then this is x squared, or x plus 1, x minus 1, so those things also have sign flipping possibilities here. So let's see, at 0 would have to try something like a half. Half squared minus 1 is negative. That would be positive. Oh, sorry, -1/2. -1/2. Focus. That's to be positive, right? And then if you plugged in +1/2, you get negative. So it's positive, negative. Looks like it has a maximum here, not a minimum. Sorry about that clumsy analysis. You can check that out again. It has a range of all real numbers. Well, let's see. The natural log of something can't ever be... let me think about that for a second. Hold on. What does this graph look like? This is x squared minus 1. The regular natural log function looks like this. So now we can never plug in numbers that are less than -1. So are you with me there? Like the smallest this can ever be is 0. So we can never get numbers, and it's the absolute value of that. So I think we're never going to be able to plug in No, I'm not convinced. I need to think about that a little bit more. What does x squared minus 1 look like? X squared minus 1 is a parabola that looks like this, right? If we take the absolute value of that, it just takes the negative part and bumps it up like this. All right? So these are all the x squared minus 1 values. Do we get a range of all real numbers? Are we plugging in all the same possible numbers? I'll have to come back to that one. So I'm pretty confident that the answer, you guys can weigh in on that and let me know what you think. But I really like this one here because look at the second derivative. This, something squared, positive, right? This, something squared plus 1, that's always positive, times -2. The second derivative is always negative, just concave down. And then it has an asymptote at x equals 0. No, I don't think so. Maybe. Let's do this. Let's take a quick look at the graph of this. This is kind of cheating, but it's getting late, so let's cheat together. So let's see. I'm just still interested in that range issue. So we want to graph the natural log of the absolute value of x squared minus 1. And let's just do our standard window. Ooh, what's going on there? Well, this could be like spiking way down, so that's hard to know. Let's that looks like will definitely go up forever. But let's check in here and set the window. Let's look at like -1 to 1. What's going on there? Oh, I guess I need to see around the -1. So let's say window from about -2 to 2. Let's try that. So it looks like I'm going to have to think about that, and it's not going to happen right now, but why the range? It looks like it's only going down to -1 and then flipping back up. So I'll have to think about that. So anyway, D is the correct answer. Okay, last one. Here, this function, domain is a set of all x, 0 to 9, then the absolute maximum value of the function occurs when x is. Well, talking about maximums, so I'm going to find the derivative, x squared minus 8x plus 12, and set it equal to 0. And that factor is real nice, don't it? So that happens at 2 and 6. But here's the deal. You cannot forget this. If it's a closed interval, then for maximums and minimums, you've got to check the endpoints also. So the candidates for absolute maximum, like the biggest value the function ever takes on, are 0, 2, 6, and 9. Okay, those are the candidates. When you plug 0 into the original function, you get -5. When you plug 2 into the original function, you get, oh, it's too late for this. Let's see, you get 8/3 minus 16 plus 24 minus 5. That's 3, 5 2/3. I'm very vaguely confident of that. Let's see, 24 minus 21 is 3 plus 2 2/3. All right, I think that's right. When you plug 6 into this, you're going to get something it's going to go back down again, and you could check that yourself. I'm not going to do it right now. You plug 9 into this, 1/3 times 9 cubed. Are you kidding me? 4 times 9 squared is 12 times 9 minus 5. Fun stuff. Let's see, that's one of the 9's gets divided by 3, so that's 3 times, and then the other 2 9's is 27. 3 times 27 is, no, sorry, that's 3 times 81. I lied. Right? 9 squared, and then the other 9 is getting chopped down to that 3. Minus 4 81's. Well, I like that. 3 81's minus 4 81 is -1 81. Plus 12 times 9 is what, 108? Right? 90 plus 18 minus 5. And let's see, 108 minus 81 is 17 minus 5 is 12. Is that right? I think. So that's the absolute maximum value. It happens when x is 9. I'm going to bed.